In this lesson, we're going to be using sum and difference identities for our trig functions, which you'll see in that box at the very top of your page, where we're basically adding two different angle measures or subtracting two different angle measures. Now, one thing I want to point out about this piece right here that I'm highlighting below, these are double angle identities, which I put on here for you guys to reference. We're not actually going to use it in this section, but we could use these when we're solving equations in our next lesson. So that's why they're on there. So if you would like to take a look at examples using double angles, feel free to take a look in your textbook section 14.5, or feel free to, contact me and I'll be happy to go over that with you. But again, that's just there on this page for your reference. Okay, but today we're focusing on just sum and difference identities and how to use them. So once you know what these identities are, right, for example, sine of A plus B equals sine A times cosine B plus cosine A times sine B, we can actually use it. So we're just going to basically be doing examples today. So if you look at the first example, we want to find the exact value of cosine 15. So that means we don't want to put it into our calculator and get this rounded decimal. We want to figure out what it actually equals. Is it, square root 3 plus square root 2? Is it square root 7 over 5, right? That's what we're trying to find out. So that means first things first, we have to think about what angles can we do sine, cosine, and tangent to where we can actually get exact values, and that's where we go back to those special right triangles, the unit circle. So we want to remember we can actually do sine, cosine, and tangent of 30, 45, and 60. Okay, so if you have your unit circle handy, we can look those up pretty quickly. So what we want to do then is take a look back at this cosine 15, and let's rewrite it using either a sum or a difference of any combination of 30, 45, and 60. So for example, for cosine 15, I might say, hey, wait a minute, 15 is equal to 45 minus 30. So why don't I rewrite this as cosine of 45 degrees minus 30 degrees? And then I can go and use that difference identity where it tells me cosine A minus B equals cosine A times cosine B plus sine A times sine B. So here my A would be 45 and my B would be 30. So then we'll get cosine of 45 times cosine of 30 plus sine of 45 times sine of 30. So what I'm going to do now is go and look at my unit circle to remember what cosine 45, cosine 30, sine 45, sine 30 are. Of course, if you have this memorized, you can go ahead and write it in. But cosine 45, if you remember, is square root 2 over 2. Cosine of 30 is square root 3 over 2. Sine of 45 is, oops, had that one off. Sine of 45 is square root 2 over 2, and sine of 30 is 1/2. And now we can actually go through and simplify and get an exact numerical answer. So remember, when we're multiplying our radicals, square root 2 times square root 3 turns to square root of 6. 2 times 2 is 4. Then we'll have square root 2 over 4, and then we can combine this on the numerator to say square root 6 plus square root 2 over 4 is what cosine of 15 is equal to. Be careful, don't make this square root of 8 or anything like that. Remember, we can't combine radicals with addition or subtraction unless they have the same radicand, so they have to have the same number inside. But that is my exact value of cosine 15. So we can go ahead and do tangent 105, same idea, break it up into some combination of adding or subtracting 35, 45, and 60, and then use that sum or difference identity depending on if you're adding or subtracting. Now, if you want to pause and try this on your own, go for it. Otherwise, keep watching and I'll walk you through tangent of 105. Okay, so when I saw tangent of 105, I broke this down to tangent of 45 plus 60, because 45 plus 60 equals 105. And then I can see, okay, I'm using a sum identity where A is 45, B is 60. So I'm going to make a fraction of tangent 45 plus tangent 60 over 1 minus tangent of 45 times tangent of 60. Now we can go to our unit circle and find tangent of 45 and 60, but remember tangent is y over x, so you do want to make sure you do that division off to the side somewhere. So if you have questions on that, definitely ask. But I went ahead and did those tangents earlier. So I got tangent of 45 is equal to 1. Tangent of 60 is equal to the square root of 3. Then we have 1 minus tangent 45 is once again 1. And tangent of 60 is square root 3. Now this should hopefully start looking like a familiar situation. This is 1 plus root 3 over 1 minus root 3. We don't like those radicals in the denominator, so let's go ahead and rationalize. So we're going to multiply by the conjugate. So 1 plus the square root of 3 in the denominator and also in the numerator. And that will allow us to get rid of the radical below. So we have basically, remember, you can put this in parentheses, the numerator and denominator in parentheses, and we can FOIL. So I'm going to get 1 plus square root 3 plus square root 3 plus 3, because the square root of 3 times the square root of 3 is square root of 9, which is 3. And then we have a difference of 2 squares here, so we can also FOIL that, or you can remember your difference of 2 squares pattern, where we'll get 1 minus 3, because it's a squared minus b squared, when you have a product of a minus b times a plus b. And then just clean that up. So now we have 2 of the same radicals, so we can go ahead and add those together. So I'm going to get 4 plus 2 square root 3 over negative 2. And then remember, you can split this up into 2 different fractions. So 4 over negative 2 plus 2 root 3 over negative 2 gives me negative 2 minus square root 3 as the exact value of tangent 105. Okay, so that's an application of how we can use our identities, and we can of course prove different identities. So we can use our identities, our sum and difference identities, to prove statements. So here, if you look at the next example, I want to prove that cosine of x minus pi is actually just negative cosine x. So remember, when you're trying to prove these identities, you're really just going to kind of mess with one side. And since we were just talking about the difference in some identities, I'm going to focus on transforming this left side. All right, so if here x is a, pi is b, we can go back and see, okay, what would I do with cosine of a minus b? Well, that's cosine a times cosine b plus sine a plus times sine b. So I can go ahead and rewrite that as cosine of x times cosine of pi plus sine of x times sine of pi, and see if that equals negative cosine x. And I forgot to do this in the other video, but remember, it never hurts to actually write down the reasoning for what you're doing when we're doing a proof. So how can we do this? It's because we're using the difference identity for cosine, right? All right, so that's your cosine difference identity. But anyway, let's go back to what I have here in blue and let's simplify what we can. So remember, pi is the same as 180, right? If you look at your unit circle, pi is also at that point negative 1, 0. So we can actually do sine, cosine, tangent of pi really easily too. So if we take a look at that, cosine of pi is the x value, so that's negative 1. So we can change cosine pi to negative 1. Sine of pi then is the y value, which is 0. Right? And then what we've done here is we've just basically evaluated cosine pi and sine pi, right? Using our unit circle. So let's go ahead and now simplify. So cosine x times negative 1 is the same thing as negative cosine x. And then sine of x times 0 is 0. So what do you know? It checks out. So we just simplify to get to that final answer, right? So both sides have to match. So that's proving the identity, okay? So let's take a look at the next example. We can kind of work our way backwards here. So if you're looking at here, we're asked to simplify sine of 3x times cosine 2x minus cosine 3x times sine of 2x. You might be wondering, wait, how can we even do that? That's not pi or 2 pi or 45, 30, or how do we actually do that? Well, we can go back and kind of match up this statement with what difference or sum identity it corresponds to. So where do we see sine times cosine minus cosine times sine? Well, if you look here, sine times cosine minus cosine times sine, that is this sine of a minus b, that difference identity for sine. So I'm going to go ahead and use that on this next example. So I'm going to remember, hey, sine of A minus B equals sine of A times cosine B minus cosine A times sine B. So then if I just work backwards and say, wait a minute, here, A is 3x, B is 2x, let me just go backwards and make this sine of A minus B. So this will become sine of 3x minus 2x, which simplifies to just plain old sine x. So we want to be comfortable going kind of both directions with our identities, okay? So finally, we want to be able to use our Pythagorean theorem with our sum and difference identities, and you might be wondering, wait, how does this a squared plus b squared equals c squared business actually tie into sum and difference? Well, let's take a look at this last example. So it's asking us to find sine of a minus b, given some information about sine of a and cosine of b. And you'll notice we are given restrictions, right? So sine of a equals 4/5 with the angle being between pi over 2 and pi. Sine of b is 3/5 with that angle being between 0 and pi over 2. So we'll talk about how that kind of comes into play. But you'll notice, hey, we're still starting off with a difference identity. We're still looking for sine of a minus b. So remember, sine of a minus b is equal to sine of a times cosine of b minus cosine of a times sine of b. So when we looked at this, we'll notice we actually have two missing values. We don't actually know what cosine of a is, right? I know sine a is 4/5, but what's cosine a? And similarly, I don't know what sine of b is. I know cosine b, but I don't know sine b. So this is actually where the Pythagorean theorem could come in handy. So let's kind of interpret the situation with the angles themselves, and then we'll come back to actually solving for sine of a minus b. Okay? So starting off with sine of a. So if we know sine of a equals 4/5, remember sine is opposite over hypotenuse. So it tells us two sides of a right triangle. But if I want to do cosine of a, cosine, remember, is adjacent over hypotenuse. So I'm missing one of the sides of my triangle. So what we want to do then is we want to use that restriction here, this pi over 2 is less than a is less than pi, to help us draw the triangle for using the reference angle for a, right? And then come up with the adjacent side. So if I'm going between pi over 2 and pi, remember that's the same thing as 90 and 180. So this would be pi over 2 and this is pi. And then that reference angle A would be with the horizontal. So A would be somewhere here. So that tells me pretty good information. If I was going to draw my right triangle, here is A, then I know the opposite of A is 4, the hypotenuse is 5, and then I can find this adjacent leg, which I'm going to call B. So use your Pythagorean theorem. 4 squared plus b squared equals 5 squared. 16 plus b squared equals 25. B squared equals 9. And b equals 3. Now, in this case, because we're in the second quadrant, we have to be very careful. If this was just a plain old triangle, sure, we'd say that's a positive 3 because that's a side length. But we're using this triangle in terms of the angle, right? We're with the reference angle. So we don't want to say b is 3, but b is actually negative 3. Because we're going to the left toward pi, okay? So b is actually going to be negative 3 because we're going to go negative 3 on the x, right, on that horizontal axis, up 4 on the vertical to get to that kind of terminal point if you look at that as a vector, okay? So that being said, we are now able to find cosine of b because remember cosine is adjacent over hypotenuse. Adjacent is negative 3, hypotenuse is 5. So, or I'm sorry, this should be cosine A, not cosine B, but cosine A is going to be negative 3/5. So now we can go ahead and substitute that in, right? Our last missing piece of information is sine B. So if you want to pause here and try that out yourself to find sine B, it's the same process using your Pythagorean theorem, finding the reference angle and the right triangle. If you want to just listen to me finish it off, go ahead and keep going. All right, so how do we deal with angle B? So cosine of B is 3/5. Cosine is adjacent over hypotenuse. So here we're given the angle is between 0 and pi over 2. So now we're looking at the first quadrant because 0 is here, pi over 2 is the same as 90. So my angle B is going to be right with that horizontal axis. So again, you can take out that right triangle, and we know if this is B, the adjacent is 3, the hypotenuse is 5, and then we need to find A, which is the opposite, which I'm labeling as the opposite. So again, you can use a Pythagorean theorem, or you'll realize we're using the same 3, 4, 5 triangle, but if you don't recognize that, that's okay. 3 squared plus a squared equals 5 squared, 9 plus a squared equals 25, a squared equals 16, and a is 4. And before we just say, okay, a is 4, we want to make sure we're looking at the direction we're going. So to look at angle B, we went to the right is positive, we went up is positive, so a is a positive 4, that's okay. Okay, so then to wrap that up, now we know 4 is the opposite, sine of B is opposite over hypotenuse. So we have all of our information now. We're going to come back to sine of A minus B and just substitute. Sine of A was given to us as 4/5. Cosine of B was given to us as 3/5. Oops, I wrote 3/3. 3/5. Minus cosine of A, which we calculated is negative 3/5. And sine of B, which is positive 4/5. And we're just going to go ahead and simplify, right? Multiply and simplify it all out. 12 over 25 minus a negative 12 over 25. Double negative turns into positive. And our final answer is 24/25. And that's it. Thanks for listening. So let me know if you have any questions.